Log on, tune in, find out. Another good idea from Cambridge.
Colton from University of Delaware will speak on transmission eigenvalues for spherically stratified media.
Okay, thank you, John. And I'd also like to thank, like everyone else, the organizers for inviting me here, and particularly with the nice weather that's been provided. I'm sure they arranged that using secret inverse methods unknown to me, but I appreciate that. There's three reasons for my talk ahead of time. It's on a particularly simple issue. The first reason is it's an introduction as simple as possible to the interior transmission problem and transmission eigenvalues. And as such, that's going to be a preparation for the talk that Alba Sacconi is going to give later on today. So this kind of gives you it's an introduction to her talk. Secondly, since it's the simplest example, it suggests possibilities for the more general case when you have a non-spherically stratified medium, and will perhaps give some ideas of what future directions in that area could be. And the third reason is purely propaganda. It's a non-self-adjoint eigenvalue problem. I'd like to get those people who are interested in spectral problems for ODEs and self-adjoint to maybe cast their eyes on some of these non-self-adjoint problems, and hopefully they could do things which I can't do. I'm no expert on inverse spectral theory. I know there are people in the audience that are, and so my hope is if I can get them interested in these kinds of problems, they can prove things which I can't. So it's a propaganda and a selfish reason. So let me start by saying where this interior transmission problem comes from. And so let's consider one of the world's simplest scattering problems. You have the velocity u plus k squared. Let's see. Is it down at the bottom here? Oh, here it is. K squared n of r u equals 0 in R3. U is the sum of a scattered wave and an incident wave. And of course, the scattered wave satisfies the summerfield radiation condition. And the incident field is assumed to be an entire solution of the Helmholtz equation. K is the wave number. N is the index of refraction, such that n of r is greater than 0, and n of r equals 1 for r greater than or equal to a. That means the scattering object is a sphere of radius a, and it's spherically stratified. And a simple question to ask is, do there exist incident fields such that the scattered field US is identically 0? For a given frequency. Do there exist frequencies such that the scattered field is identically 0? So in some sense, this is kind of like the dual problem to a cloaking problem in some ways. There you say, can we design an index of refraction so that for a given set of waves, you have no scattered wave? Here we have a fixed index of refraction, and we're trying to find an incident wave that doesn't scatter. And the problem is, in the spherically stratified case, is very easy. The answer is yes, provided there exists a non-trivial solution to this interior transmission problem, which I write differently than John. In my case, you have two elliptic equations, here and here, and they're linked by the Cauchy data on the boundary. And here B is a ball of radius A. So do there exist situations where you get a non-trivial solution to that problem? And because we have spherically stratification, this problem is very easy to answer. You just separate variables. And if you separate variables, the radial part satisfies this equation here, and we'll normalize the radial part so it looks like a Bessel function at the origin. That's just to normalize it. There's nothing special about that. It just fixes it. And here JL is a spherical Bessel function. And it's easy to check out that there exists a non-trivial solution to the interior transmission problem, provided there exists constant K and L, or AL and BL, not both 0, such that this system of equations is satisfied. That's just separation of variables. Here L is an integer, so you separate variables, and that L corresponds to the separation of variables parameter. And so that's a very easy question to answer. Non-trivial solution to the interior transmission problem exists provided that this determinant is 0. Now, of course, there's no a priori reason. It could be that that's identically 0, but if it's not identically 0, it's clearly an entire function, and therefore it has a discrete set of k values. So in other words, if this isn't identically zero, there can only be special values of k for which there is no scattering. And the incident field in that case would be the spherical Bessel function times a spherical harmonic. If you sent that field in, there'd be, and you had k such that this determinant was zero, there'd be no scattered field. And so the question is, when is that possible? What can you say about these transmission eigenvalues? And since you have a nice entire function here, just like you often do in the theory of inverse spectral theory for self-adjoint problems, such as, for example, in Andreas Kirsch's book on inverse problems, using an entire function, analytic function theory is a good way to at least begin to look at these kinds of problems. And in this case, so what I want to do, again, to remind you, the transmission eigenvalues of values of k for z at 0. And to investigate this, the following theorem is basic, which is, people know, but I'll state it in the form to remind you. It's Hadamard's famous factorization theorem. You have an entire function of exponential type with 0 zn such that the sum of the reciprocal of the zeros and absolute values is infinity. Then you can represent the entire function in this form. And again, I have exponential type, so there's just a z to the 1 here. This z to the k corresponds to possible zeros at the origin, and here's the zeros of the entire function, and you see k, a, and constant. So the first question to ask in a spherically symmetric case is, do there exist transmission eigenvalues? Now, for the non-spherically stratified case, as you'll hear from Professor Sacconi and was mentioned by John Sylvester, and will probably be mentioned by Andreas Kirsch, it's only recently that transmission eigenvalues were shown to exist. And that was first done by Professor Lassi Pavrienta and John Sylvester, and then improved upon by Sacconi and Gentidis and Hadar. And that put the whole business of the interior transmission problem, revived it, so to speak. In other words, until that time, those of us looking at scattering problems, using this linear sampling method and factorization, we tried to avoid transmission eigenvalues. And so once we showed they were discrete, we said, fine, there are not too many of them, and we said, thank goodness they're discrete, and we moved on. The fact that they existed now taught us, well, maybe we should find out more about these things. And that more will be said about that when Sacconi's lecture. But the first thing in the spherically stratified case is pretty easy. So the theorem says, assume n of r is not identically equal to 1, then there exists at least a countably infinite number of transmission eigenvalues. So in this case, remember, those of you remember John Sylvester's talk, when n changes sign, you had to assume as n was constant near the boundary, then you could show there was a discrete, but the existence question is still open. But when you have a spherically stratified case, you don't have to make any assumption on whether n is bigger than 1 or less than 1. It's just, as long as it's not identically 1, there exists a countably infinite number of transmission eigenvalues. So it'd be interesting, is that true in the general case or not? This suggests that it might be, but who knows? And the proof, just to give you a taste of the proof, and how Hadamard factorization comes in, you can easily show that this determinant is an entire function of k, of exponential type. It's bounded on the real axis, positive real axis. It's an even function of k, and d of 0, 0 for any L. Those are just trivial things you can note. And so therefore, if this determinant does not have a countably infinite number of zeros, you conclude by the Hadamard factorization theorem it must be identically 0, because then all that's left is a z. It has to vanish. There's a power of z times e to the az. So even if a is complex, it's not going to be bounded. So there's going to have to be an infinite number of zeros. So the question is, although it may seem unusual, can these determinants vanish for every L? And maybe it's identically 0. That's a possibility. That says the constant in front of the Hadamard factorization theorem is 0. But if that were the case, you could easily derive this identity, which I won't go through, but that's a relationship between the YLs and the JLs. And M here is always 1 minus n. And then if you let k go to 0, you get this identity for every integer L, and therefore by Munch's theorem, M must be identically 0. And so that proves it. So it's just a very simple proof to show there exist transmission eigenvalues in this case. And that's one of the pleasures of working in spherically stratified case. You can get results very easily. So the problem of showing existence of transmission eigenvalues in the general case, that's not so easy. I mean, of course, it's easy once you see how it's done, but it's not so easy before you see how it's done. But in this case, it's pretty simple. So now that we know how they exist, Incidentally, I should mention that's one of the reasons probably there's a 20-year gap between showing the discreteness of transmission eigenvalues and the existence. People were very reluctant to talk about transmission eigenvalues if they didn't know they even existed, because it wasn't too nice to prove lots of theorems about something which may not even exist, and so that caused people to steer away. But those times are over. Now, let's go a bit further. Let's assume now n of r is bigger than 1 or maybe less than 1. And let's assume it doesn't change sign. Then you can easily establish this asymptotic relation for the determinant. And in this case, you can easily see that there exists an infinite number of real transmission eigenvalues. And furthermore, this set of eigenvalues is discrete. It's very easy to see here because as k gets large, obviously the sign function vanishes. And so you can easily see there exists a discrete number. Now, of course, you have to make sure that this argument here isn't identically 0. So if n changes sign such that this integral happens to be equal to a, well then this whole argument breaks down. So the question is, do transmission eigenvalues form a discrete set in the case when n of r is simply not identically equal to 1? So in other words, this can change sign. That's just an open question, which I would think it could probably be very easily answered. So again, another purpose of this talk is I'm going to suggest a number of open problems, which I've thought a little bit about but couldn't do. That should in no way whatsoever intimidate anybody. There may be some very easy way to do it, and if so, that would be nice to get some of these things out of the road. So in this particular case, when n is bounded away from 1, then you have an infinite set of real eigenvalues. Now, the next question to ask is, where are these located? At the moment, there may be complex eigenvalues, there may not. We know there exists an infinite number of eigenvalues, and in the case when n is bounded away from 1, there exist some real ones, but there may be some complex ones. And one way to look at that, where they are, is to use a theorem called Karlmann's theorem. And Karlmann's theorem says that if f of z is an entire function of exponential type, with zeros such that this is true, and now if n is bigger than 1 or less than 1, we know that's true by this asymptotics, then if f of z is bound in the real axis for epsilon greater than 0, the zeros that lie outside of these small sectors have to be such that it's less infinity. So that means in some sense, most of the zeros lie on the real axis, or near the real axis. And now our determinant exactly fits into Karlmann's theorem. So we can easily say the following. From Karlmann's theorem follows that except for a set of zero density, in the complex variables language, that means that all the zeros of these determinants for each L must lie in an arbitrarily small angle near the real axis. So right in here, no matter how small this epsilon is. So there may be a few outside. Now this is, in the more general case where you have non-spherically stratified medium, there's a paper by Lassi Pavrienta, and I won't try to give all three of the other people on the paper. There you are. You heard from the horse's mouth, and we show that all these the eigenvalues lie in a parabola. And so this just says for fixed L it's there. So the open problem here is, can you say, except for a possibly set of zero density, do all the transmission eigenvalues lie in this wedge? For each fixed L, they do, but maybe if you add up all these L's together, of course, this may be violated by and by. So my guess is that's probably true, but I have no way of proving it, and again, it seems like it shouldn't be overwhelmingly difficult to prove, but I again leave that to you as an open issue. And of course, it's very much an open issue to ask whether that's true for the case when n of r is no longer spherically stratified. But it suggests that something like that may be true, except for a set of zeros such that this is true, maybe they all lie near the real axis. That would be my guess at the moment, but I don't know. Now, moving on. We've showed that transmission eigenvalues exist. We've showed that they all lie near the real axis, but maybe they're all in the real axis. The question is whether complex eigenvalues exist or not. And at the moment, the only case where that, well, let me start over again. Until very recently, there's no idea at all. And up to now, I've told you, at least in the abstract, that this problem is not self-adjoint. But if you look at it, some of you might not immediately identify that why it's not self-adjoint. I mean, it looks pretty benign, but one way to convince you that it's not self-adjoint is to show you there exist complex eigenvalues. There are other ways, but my favorite way is to show you the complex eigenvalues that no one's going to argue with me that it's self-adjoint, I would hope. So, as I said, at the moment it's not known in the general case at all, but we can do something in the case of when n's a constant. And so let me just tell you how that works to convince you there exist complex eigenvalues. So let's look here. Very simple. Let's get a two-dimensional interior transmission problem for the disk. So here's our two-dimensional interior problem, and n in this case is a constant. And I want to show you, first off, for n small enough, there exist complex eigenvalues. Well, K real transmission eigenvalue provided this determinant is 0. That's the same determinant we have, only it's the R2 version of the determinant. And if you like special functions, you'll immediately recognize that that's this. You can represent it as that integral. In fact, you can get that, it just comes from the differential equation, actually, so there's nothing particularly deep, where J0 and J1 are Bessel functions up here. And then if you look at this limit, this analytic function of k, you'll see that in the limit you get this, which is not 0. But k squared times k to the minus 2 is f of k is an even entire function of exponential type that is bounded on the real axis. And since by Hadamard's factorization theorem, k minus 2 f of k has an infinite number of zeros, but all these zeros must be complex because there are no real zeros. It's not equal. This is obviously. So since they all must be complex, from Hurwitz's theorem, d0 k has a complex zero of n's close enough to 1. So again, it's a nice example. If you look at this, especially spherically stratified case, there's all kinds of opportunities to use different theorems from analytic function theory. And so for those people who love analytic function theory like I do, it's a nice place to relive one's youth and use analytic function theory. So that says at least for n small enough, that's true. Now what about for general n? Well, it's possible to say more. In particular, one can see from that formula I just gave you, which is true for all, I'll go back one, this formula here. That's true for any constant n. So it's, oh, sorry, I'm going to. The d0 of k equals 0 only if j0 of nk equals 0 or j0 of k equals 0. Now, the theorem you want to use now is a theorem of Laguerre, which is a generalization of Rolle's theorem to entire functions. And Laguerre's theorem says if you use this theorem, you can conclude that for n greater than 0 and n not equal to 1, d0 of k has an infinite number of complex zeros. So for any complex n, any constant n, there exists an infinite number of complex transmission eigenvalues, in this case of R2. And I'm not going to go through the proof. It's Laguerre's theorem is the basis of it, but there's a lot of calculus manipulation. But Laguerre's theorem, which I'm sure most of you didn't know, because this is a result really due to a colleague of mine in Delaware called Y.J. Leung, who's a student of Peter Duran, and is a very smart guy in function theory. He reminded me of Laguerre's theorem, which I had seen a long time ago but forgot. But Laguerre's theorem says that f of z be an entire function of order less than 2, such that f of z is real for real z and has only real zeros. And the zeros of f prime are also real, and of course, and they're real and are separated from each other by the zeros of f of z. But you can give counterexamples that if f of z is of order 2, that's not true. You can have real zeros, you take a derivative, you'll find some complex zeros. So it's at first glance you say, well, that's always true. But remember, the key thing is here that f prime has only real zeros, and they're in between the real zeros of form. If you use this theorem, this says something about what happens if you have a function that has no complex zeros. You can use this, as you might imagine, to show that you get a contradiction, so therefore it must be an infinite number of complex eigenvalues. That's how you use that. And a big open problem, first off, even in the spherically stratified case, there exist complex transmission eigenvalues. Now, we're currently still working on that, and we have some tentative results, but they're not ready. We haven't checked the proofs out, but roughly what it says is they're what we would call in the United States as half-assed results. They're not too good. It says, for example, if n of 1 is a rational number, then there exists an infinite number of complex eigenvalues. We can prove theorems like that. And you would think maybe by some kind of continuity argument you could get the result for n of r, but that's not clear. And of course, the case for general n of x, no one has any idea. So that's whether it exists complex eigenvalues or not. So this is another open problem. And as I said, the other open problems I gave you, I have no idea how to do. But this open problem, at least I have some idea under very special circumstances on what n of 1 is like. That's the boundary of the ball. So we now know, at least in this case of constant n, there's complex eigenvalues. I hope that convinces you the problem is not self-adjoint. Now, for most of the rest of the talk, I like to talk about inverse spectral problems. So now that we know that transmission eigenvalues exist, do the transmission eigenvalues uniquely determine n of r? That's the spectral problem. There have been a number of at least one paper that addressed itself to that problem, and that was a paper by Joyce McLaughlin and Polikoff some time ago. And they showed they solved the inverse spectral problem in that case, but their assumption was that there only existed at most a finite number of complex transmission eigenvalues. But as you've seen, at least in the constant case, there are an infinite number of them. So it's not at all clear whether that assumption is valid or not. And if it's not valid, of course, the theorem is not valid either. That's no reflection on the paper per se. These things happen, as my mother used to say, in the best of families. But it does show that, and they use only the real transmission eigenvalues. That was the idea. So let me first talk about this recent result of Atkinson, Tutitis, and Papanikolaou. That's not your Papanikolaou. It's another Papanikolaou, right? They consider the inverse spectral problem corresponding to transmission eigenvalues having spherically symmetric eigenfunctions. So that means they're only going to consider the transmission eigenvalues corresponding to d0 of k. The transmission eigenvalues have axisymmetric solutions. And the first thing that and incidentally, this paper hasn't even been published yet. It's been submitted, and hopefully it'll be accepted at some point or another. So the first term to ask is, remember, d of 0k could be identically 0. We showed if it's not identically 0, then the zeros are transmission eigenvalues, but there's nothing automatically to rule out the fact that determinant is identically 0. So the first thing they had to show was that they wanted to show that if dk0 is identically 0, that n of r must be 1. If n of r isn't 1, then d0k is an entire non-trivial entire function, and there's this transmission eigenvalues. So this is basically saying that axisymmetric transmission eigenvalues exist. And the proof is kind of nice. Slight misspelling of words here. But suppose this determinant is 0, and then you set y0 over yr over r, and then you get that y double prime plus k squared n of r y equals 0, and these initial conditions. And since the spherical Bessel function is sine kr over kr, d0k in fact is this. Then if d0k is 0, then an argument that takes about half a page and is based on an argument involving entire functions, not obvious, you can show that y of a must be sine k over ka, and y prime of a equals cosine ka. And hopefully, if I didn't make a mistake, that obviously works, but that's the only solution. Okay, so you can determine what y of a is and y prime of a. I may have it. I'm not sure I have a. I think I may need an A here, but I'm not sure. So I may have to modify that. If that's the case, that means the spectra of these two Sturm-Liouville problems right here are the same as that for n of r equals 1. Because if you look back here, we have the y of a and y prime of a are the same as the data for the spectral problem for n of r equals 1, and therefore, by uniqueness of the inverse Sturm-Liouville problem, n of r equals 1. So it's in my mind, it's a rather complicated proof of what should be a very trivial result. I mean, it seems to me that you should be able to show d0 of k is not identically 0 by some pretty elementary means without invoking the whole inverse Sturm-Liouville problem, which is a lot of heavy machinery. Remember, this also is inverse Sturm-Liouville problem that Krein looked at. You know, it's k squared n of r. It's not the k squared minus n of r. So it invokes quite a bit of heavy machinery in order to do it, but nevertheless, it's a nice connection with that problem. And then they showed further, using that basic idea, that if n of r is less than 1, then the transmission eigenvalues correspond to spherically symmetric solutions of the interior transmission problem uniquely determine n of r. But here, when they say that, they're including the complex transmission eigenvalues. If you exclude the complex transmission eigenvalues, then it's highly unlikely that it will uniquely determine n of r. But if you consider all of them, then you have that. Now, unfortunately, the proof just doesn't work for n of r bigger than 1. This is, at first glance, this condition that n of r is bigger than 1 and less than 1 seems rather artificial, because what it would mean physically would just mean, if you're thinking about electromagnetism, for example, that the permittivity is greater inside than outside. This is, in one case, or it's less than inside than outside, which seems like shouldn't impose draconian conditions on the mathematics. But here, it appears that's the case, but of course, who knows? Maybe just because this proof breaks down if n of r is greater than 1, analogous proof would be true by a different proof. But I'll show you now what we have what kind of thing we can establish for n of r bigger than 1. It's not nearly as good as what they have. I mean, the theorem is much more, this inverse spectral theorem is not, it involves using the eigenvalues of all the transmission eigenvalues, not just the ones corresponding to spherically symmetric eigenfunctions. I'll show you how that works. To do this, we have to get some asymptotics for these y L of r as k tends to 0. And this is a problem here, because for those of you who use asymptotics, it's not trivial if you're given a solution of an ordinary differential equation with given initial conditions to find the asymptotic behavior for k at infinity and k equals 0 both. I mean, that means you essentially know everything about it, just about. So usually you can get one, but it's hard to get the other. It depends on how they usually have quite different methods are involved. So for example, if you're looking at asymptotics for Bessel functions, the power series tells you the low frequency asymptotics, and then you use stationary phase and integral representation to get high frequency. But if you have a general ODE, trying to get those similar relations is not so easy, because you don't have typically either one of those to work with. So we do need behavior. We already have, remember, for n of r bigger than 1 or less than 1, we have the asymptotics of YL for large k. Now we want the asymptotics for YL for small k. And that's what you can do, an easy form to do. This is a result of Reiner Kress and myself, which we did. Pardon? Yeah, these are like Gilfan-Levitan operators, right? Yeah, they're very closely related. Sure, yeah, right. But this particular representation was due to Reiner and myself 10,000 years ago when he first came to Strathclyde, and we tried to find something to work on. We thought we'd never ever use it again, but we did. And here, yeah, it's like a Gilfan-Levitan operator, and this G satisfies this Goursat problem, and G on the characteristic R equals S satisfies this, and when R and S are 0, it's 0. And here again, m is n equals 1 minus n. So you have this integral operator, provided you can find a G satisfying this highly singular hyperbolic equation. Right? It's singular here and here, and well, everywhere. And you can easily do that. You can get G by, I have plenty of time, by iteration. And it's an even function of k, an entire function of exponential type, satisfying this condition here. So for small k, you have this representation. So the idea again is you take that singular Goursat problem for that hyperbolic equation. So what we have here is a singular Goursat problem for this equation, and you simply make a change of variables and solve it by iteration. So it's relatively straightforward. It's not anything sophisticated, but you get that operator, and from that, for the representation formula, you immediately get that the y of L of R behaves like this. So when you look at these problems with this ODE, this capital YL, it's not too difficult to show that in the low frequency K it looks like a spherical Bessel function. I mean, we defined it for R going to 0, it looked like this. It's not too difficult to show that for K going to 0, you also get this. What's more difficult is to get this extra term here, this term right here. But you can get that, and of course, this JL has some higher powers of K, which by right should get lumped into the big O term, but I kept it here just so you can see where the Bessel functions come in. So now that we have that, I'm going to show you what we can do now to obtain this inverse spectral theorem. Let C2L plus 2 be the coefficient of K2L plus 2 in the Taylor expansion of DL of K. We're not going to, this procedure I'm going to give you is not at all computational. It's purely existence. But let this be the coefficient of K2L plus 2. And then from that asymptotic expansion I just gave you, you can easily show that C2L plus 2 equals this. So in other words, this is the thing we're looking for. Remember, M is 1 minus N. So that's expressed in terms of this C2L plus 2. And by Hadamard's factorization theorem, again, we have DL of K equals this. So we're assuming that we know the transmission eigenvalues for each L. So we know this infinite product in principle. So we know everything except this constant. So the Ki, and I've rewritten this because the determinant is even, so I can rewrite it as a product just over the eigenvalues in the right half plane. That got rid of that exponential e to the minus z over e to the minus k over kn. So I have this. Of course, I don't know what the C2L plus 2 is, but what you can show from the asymptotic expansion of the DL of K as K goes to infinity, you can show two things. One, that coefficient C2L plus 2 is not 0. That is actually is a non-zero. And furthermore, that the ratio of this looks like this. That came from the asymptotes I gave you a long time ago for the YLs. And this gamma sub L is this number here. And so you put that together, you find out that that's true. That's just a manipulation of these identities. So in other words, if you know it for all L, and if you know n of 0, this gamma L is known from the fact that the infinite product, since that's an entire function, presumably it has an asymptotic behavior, and you can determine this gamma of L. Okay, so this right-hand side is all known. So that's but the reason why it's not at all constructive is that gamma of L depends on what the asymptotics of this are for large K. This entire function, you know exactly the form except for a constant, and that constant happens to be gamma L, but trying to compute it, of course, is not possible. So you have this, and therefore, from coming back here, you have Munch's theorem again, and uniquely determined that if you have two of them, then and n of 0 is the same, then m must be 0. So the inverse spectral problem is the following, and that's in a recent paper of Sacconi and myself and Tentitas. If n of 0 is given, and n of r is bigger than 1, then n of r is uniquely determined from a knowledge of the transmission eigenvalues. So again, all of them. So it's a much weaker result than the result for n less than 1. N less than 1 said you only consider the axisymmetric eigenfunctions. Here you have to consider all the eigenfunctions, plus you have to know what n of 0 is apparently. So the question is, if n of r is bigger than 1, do the transmission eigenvalues correspond to the spherically symmetric solutions of the interior transmission problem uniquely determine n of r? In other words, is there a theorem for n of r less than 1 that would be good for n of r bigger than 1? And, you know, my guess would be yes. I think this is a rather artificial way of proving this theorem. In other words, we proved this theorem here using the tools we had in our toolbox. And the tools we had weren't designed for this problem. And so if you try to build something with the wrong tools, you get a rather awkward theorem. That's how I look at it. I think the answer to this problem is yes, but again, I have no idea. That certainly the proof for the case n of r less than 1 does not work. That's clear. There's no way you can repair that if you look at that proof. And so it'd have to be some different proof, but again, it may be just looking at the proof for n of r less than 1 in the right way, and perhaps it's easy. So that's, for the time being, that's all I want to say on that problem. And I want to finish with the case of absorbing medium, which is even more non-self-adjoint, right? Because now we're going to allow complex coefficients. So no one would argue that this problem is not self-adjoint. So in other words, this would correspond to the scattering problem where you have a medium which has absorption and it's placed inside another absorbing medium, so which we'll assume is constant. You have to answer your question?
I'm just wondering, you have to be a square. So your large bracket n1r plus the imaginary part.
Yeah. I mean, my n1 my n1 is the physicist n1 squared.
Oh, I see. Yeah.
And John Sylvester said, Colton, I knew this was going to happen to you. Right. This should be, this is the index refraction. So if you didn't have any absorption, this would be epsilon over epsilon naught, relative permittivity. Okay. But I'm adopting the mathematician's prerogative by not putting squares on anything, which may not be appropriate, but that's, yeah. Pardon?
K squared.
What?
K squared.
Right, okay.
Okay. Good compromise.
Could be lambda.
In physics, it's epsilon. Why don't you call it epsilon? The permittivity.
That's true. I could do that.
Then there's no confusion.
That's true.
Yeah.
Right. I'm not sure how to answer that question, except to say. Sorry. Right. Thank you, Lal. Sorry. Right. That's okay. You'll be happy to know that your influence has helped someone else down the road. So I'm going to a conference in Naples, which is a purely engineering conference, and I'm going to talk on not this problem, but a related problem where I call it n. I guess I better change that to n squared. Otherwise, I'm going to have
You use epsilon.
or epsilon. Yeah. But I do like n though. Okay.
But epsilon is small for mathematics. Epsilon is small for mathematics. Here it is not.
See, in LaTeX there are two types of epsilon.
I know.
Yeah.
But you can never be then on Blackboard.
Perhaps this perplexing problem can be delayed to a bit later. Okay, so here's the absorbing media, and here's outside where you have constant some absorption. And again, this is the Fourier transmission problem when you have absorption. And again, B is a ball, and N1 of R are a continuous function of B such that they're continuous across the boundary. Okay? And let's just look and see what happens. In the simplest case, we have axisymmetric solutions. So in this case, you have the following asymptotic behavior for large K. The asymptotics here are not nearly so straightforward as when you don't have absorption. As you can see, it gets a more elaborate nature when you have absorption, but that's what the asymptotics turn out to be. And from the expansion, you can get the following theorem. If, by some chance, you have the relation between the absorption outside and the absorption inside, together with the real part, and also that's not true, then there exists an infinite number of real transmission eigenvalues, but if this first condition is not met, there exists an infinite number of complex eigenvalues. So in certain situations, if you, for example, if you took a absorbing media and immersed it in just the right type of media with constant absorption, that's such that this held true, then you get some real eigenvalues. And the reason, of course, you're interested in real eigenvalues are those are the things you can measure from scattering data. So you'd like to say, you'd like to make use of that fact somehow or another. So if you were in a fantasy world and talked about non-destructive testing, you would immerse this material in an appropriate absorbing background media, and if you had real eigenvalues, that would tell you something about the index refraction and known medium. So even if you have absorption, in some cases you can have real eigenvalues, and of course the question is, if you don't have this condition, do there exist real eigenvalues anyway? This would be kind of the analogous question, do there exist complex eigenvalues in the other case? And no one knows anything about that. And the last open problem I'll leave you with, this is my last slide, is under what conditions do the transmission eigenvalues from absorbing media uniquely determine both the N1 and the gamma 1, both the real and imaginary part of the index of refraction? Okay, we talk about the relative permittivity. So let me just say one comment, one more minute. I tried doing that the same way I did the other case, and I got stuck on the asymptotics. You know, you have to have the asymptotics for a singular ODE, which has a term gamma over k in it, and that just messed me up. So I'm sure if someone knows more about asymptotics than I do, the problem is probably pretty easy. But I'm assuming the answer is yes, but I don't know how to do it. So that's what I have to say about transmission eigenvalues for spherically stratified media. I hope that gives you some background information where you can find out more what happens in the case when N of R is no longer spherically stratified, when for Albert-Sacconi talks this afternoon. There is many interesting problems there as there are here, and I do hope that those people who do inverse spectral theory, Malcolm, and various other people will start becoming interested in these kinds of things, because I think there's a lot of interesting problems there to look at, and they have, and particularly if you love analytic function theory, this is the place for you. So thank you very much.
Questions?
Well, did I understand right that you consider all angular momenta L, and your full set of transactions?
That's right, yeah.
It's just set for every.
Right, it's a lot of information,
It's
right?
a lot of it.
Yeah, the only case where you don't have to do that is the case with n's less than 1.
Enough, I
What?
think.
Yeah, no, you should have only that. Well, that's what I've been saying. You would think that the transmission eigenvalue just for the spherically symmetric case would be enough. That's the case for n less than 1, but I can't do anything more for n bigger than 1.
Well, and then related technical question. If I remember right, my youth, this equation with k squared, n squared, you can, by changing dependent function,
Sure, yeah. Mhm.
reduce the Schrödinger equation.
You're right. You can. In fact, that's how we got the asymptotics.
Then what will be the meaning of this transmission eigenvalues for Schrödinger equation?
Oh, that's yeah. That I don't know. That would be, I don't know, because the there in the case of Schrödinger's equation, of course, the potential decays is no longer compactly supported. So that'd be a very good question. I don't know what that would correspond to physically for Schrödinger's equation.
I think it will be very illuminating to understand, because we do know how to reconstruct potential from eigenvalues.
Yeah, right.
So that's connection of these things.
Right. Well, these are different eigenvalues, not these eigenvalues.
Yeah,
Right.
yeah.
No, it would be. Yeah, that would be a good thing to. I think lots of you've done some problems with that on
Yeah,
Schrödinger's
but then
equation.
so that at least the same way for this acoustical equation, they exist and form a discrete set when the scattering amplitude vanishes, and even for non-spherical symmetric case.
That's nice.
Yes. So what do you
But
mean?
then, of course, the inverse, the spectral problem, the real problem, and we tried hard, but we couldn't do anything.
Yeah.
Just maybe two things. So one is, so if your n, which is in physics the epsilon, if that is negative, then you have a metal, right?
Oh,
Less than 1, not negative.
Not negative.
Why not
Here
negative?
written it n squared.
That would be a metamaterial or something, right?
No, a metal. So a metal has a negative epsilon,
No,
which in your notation is a negative n.
no. N is it'd be epsilon over epsilon. It'd be the relative permittivity. So it's either be less than 1 or bigger than 1. It's not going to be negative.
Of course, it's negative. In metals, it's negative. That's what what does make a mirror made of silver reflective,
Oh.
because the epsilon is negative in the metal, and
Okay, that's news. I thought permittivity.
Be self-adjoint.
What?
If the epsilon, for example, is negative, might be self-adjoint actually because
Yeah, yeah, right.
might.
Yeah, that's
So if you have those, if you consider that case, so that your n
is
which-
negative.
which is the
Okay.
epsilon, is
Mhm.
negative, then what you're getting are so-called plasmons, so these resonances.
Okay.
And for example, they make the colors in stained glass windows. So there are metal particles that are included in the glass. And when you illuminate them, so they're very absorptive at these resonances, and therefore they can color glass. And so that's an application of these eigenvalues.
Oh, that's
I know of,
interesting.
and,
Yeah.
but I know this only for the negative case.
Oh, that's interesting. I thought.
The other suggestion is so the case you consider, that is of dielectrics, so
Mhm.
where the epsilon is positive and larger than 1.
Mm-hmm.
And the question is, I mean, there are also so-called whispering gallery modes. So
Mhm.
if you have, for example, a glass sphere, then you can guide light very well on the surface of these spheres, and they have extremely high Q factors. And in fact, so the most efficient resonators for light you can make are little tiny spheres of glass.
Mm-hmm.
And these also, they have to be eigenvalues of the Helmholtz equation.
But I thought these are these not eigenvalues of the complex poles of the scattering matrix, right?
Yeah, well, that's resonance.
They're
Resonances,
so
right.
there is- so
There's something different, I think. Though.
No. I mean, these are localized light fields. So for certain frequencies, they are trapped on the surface of the sphere. So the light is going round and round
Mhm.
forever. It's very
Mhm.
well confined. And I presume that those modes correspond to your, or the eigenvalues correspond to the eigenvalues you're considering.
I'm not sure. I think those eigenvalues, as I said, correspond to poles of the scattering matrix near the real axis, I think. Yeah.
Which will be not combined.
But these would not be transmission eigenvalues. They'd be eigenvalues, but not these transmission eigenvalues.
They're perfectly normal wave functions. They're confined. Typically, they're confined close to the interface. So
Mhm.
they live on the surface of the glass.
Maybe we should talk about that afterwards. I always identify these whispering modes as connected with the poles of the scattering matrix,
That's what I usually say.
which are different than transmission eigenvalues.
Okay, so we'll thank the speaker. I think we should hold the rest for later.
Thank you very much.